Okay, good afternoon everyone. So we will start our seminar today. So we will talk about the radiation effects in the small satellites. Our presenter is a PhD student, Husseinat, and she's also working the Leopard project, and she will talk about her research related topic today. So please ask any questions.
Hello and good afternoon, everybody. As introduced by Dr. Ojer, my name is Husseinat and I'm a PhD student in Asami Sensei's Embedded Systems Lab, and I'll present on my current understanding of radiation effects in small satellites today. So we will go through the space radiation environment, the physical mechanisms behind single event upsets, their impact on small satellite subsystems, the factors influencing their susceptibility, practical mitigation techniques, and finally the current challenges and future directions. When a small satellite is launched into space, it is exacted upon by many different types of elements that make up the space radiation environment. The sources that dominate the orbital radiation field are trapped energetic electrons and protons in the Earth's magnetic field, high energy nuclei with high linear energy transfer from outside the solar system transported by cosmic galactic rays, and sporadic bursts of protons and heavier ions caused by coronal mass ejections. In regards to trapped radiation, the Van Allen's belt is the main perpetrator in capturing the elements. The inner belt contains energetic protons closer to Earth, while the outer belt contains electrons at higher altitudes, moving at velocities around 10% the speed of light. The South Atlantic anomaly caused by the misalignment of the Earth's rotational axis and its magnetic axis allows the inner belt to reach down to low Earth orbit altitudes over the South Atlantic. When considering the survivability of small spacecraft in order to achieve its mission in this kind of environment, the budget constraints of all subsystems have to be microscoped, as tight mass budgets leave little margin for structural shielding. Reliance on commercial off-the-shelf components that are not radiation hardened result in more upset-prone systems. Fewer redundancy options and smaller power budgets mean single-point failures propagate faster, and quick development cycles also mean less time for radiation testing. So what does this all actually culminate to in the phenomenon of single event upsets in the electronics of small spacecraft? First, we'll look at the single event effect family tree. The 5 classifications fall within recoverable and potentially destructive errors caused by a single energetic particle strike. The recoverable errors being single event upsets caused by bit flips in memory or register, single event transients caused by a temporary voltage glitch that spreads through combinational logic, and single event functional interrupts caused by loss in functionality. And the potentially destructive ones being single event latch-ups that are that are caused by particle strikes turning unintended parasitic thyristors and creating low impedance short circuits between the power and the ground, and single event burnout or single event gate rupture, which triggers catastrophic short circuits causing permanent physical damage. It is this burnout and gate rupture that is the most permanently damaging type of effect. There are 2 methods for charge deposition by a particle strike: direct ionization and indirect ionization. Direct ionization occurs when heavy ions pass directly through the silicon, and indirect ionization occurs when a proton or a neutron has a nuclear reaction within the silicon with a silicon atom and then produces a secondary ion that deposits the charge locally. So when discussing single event effect mechanisms, key considerations are the linear energy transfer, which we've already seen quite a bit in these slides, and that is the energy deposited per unit path by an ionizing particle. The critical charge, which is the minimum charge deposited by a particle strike that is needed to flip the node's stored logic state, and then the sensitive volume, which is a region where the energy deposition from the ionizing particle can affect the operation of a device. Hardware technology miniaturization has led to a general increase in per-bit upset susceptibility that propagates through simultaneous charge deposition, multiple bit upsets by one particle, and lower critical charge needed to cause the upsets. So how does all of this affect the small satellites that we develop? From flipped instructions on the onboard computer to missing packets from bit errors in the protocol state machine of the communication subsystem, single event upsets affect each subsystem differently. So for ADCS, which is the attitude determination and control subsystem, it can manifest as pointing loss from corrupted attitude solutions. For the electrical power subsystem, it can manifest as misaligned power rails. And for the payloads, it can show up in a loss of data integrity. So when looking through research on orbit anomaly patterns that have been attributed to single event upsets, Michigan Exploration Lab documented a hybrid linear/circular watchdog architecture that was deployed across multiple nanosatellite missions. And this triggered critical reboots and power cycles from restart curable faults. For telemetry glitches, we have EarSat, which is Ireland's first satellite that used real flight telemetry to train and validate anomaly detection models. For the FPGA configuration errors, there are two. On the ISS, there were two quad modular redundant FPGA payloads that flew for about 13 months, and one of them experienced a rare multi-core fault that was created from configuration memory SEUs, which the team then reproduced on the ground to see how it propagated. And students of the Physical Science and Technology department in Guangxin University in China developed recently, within I think the last year, a graded SEU protection sequence, which falls under this safe mode entries. And they found that the soft error mitigation, once it exceeded a threshold, the high voltage is disabled, and then the payload enters a safe shutdown, and then the ground is alerted for the reset. Now we'll look at why not all the bits are created equal. On the hardware level, process nodes, memory type, layout, and voltage margins all shift how easily a strike can flip a bit. For process nodes, for example, small features generally lowers the critical charge, which raises the sensitivity per bit, even when the cross-section of the physical device shrinks. For operating voltages and margins, the lower the core voltage, the lower the critical charge, which reduces the design margin and narrows the gap between the nominal and the upset triggering charge. So for shrinking, for these device level drivers, shrinking the node does not uniformly help. It lowers the critical charge, but that often outweighs the smaller physical target. So we measure susceptibility, which is, I keep saying this word, but basically it's how the probability of the device going through this upset. So we measure this through beam tests, and the linear energy transfer and saturation cross-section are the two main numbers that matter most for mission risk calculations. So this graph is called the Weibull fit, and it's the shape that we use to detect how sharp the rise is between the threshold and the saturation of the upsets. So susceptibility is not just about the chip itself. Orbit, shielding, and solar cycle, and also mission duration all scale the real-world upset rates. In terms of altitude and inclination, a high altitude and polar orbits see more trapped particles and galactic cosmic ray exposure than lower inclination, low Earth orbits. And for mission duration, the longer missions accumulate more total dose and more opportunities for a rare high linear energy transfer strike, which raises the cumulative risk. The solar max cuts two ways in terms of the solar cycle phases. The more solar particle events, there are more solar particle events, but then also less galactic cosmic ray background. So now that we know why upsets happen and what we can do, we need to look at what we can do about them. And the main thing to come away from this is that no single technique is a complete solution. So the next few slides are going to be explained as a stack rather than like an individual technique. So each layer catches what the one above missed. So we start with the hardware redundancy, then the error detection and control, watchdog timers, fault-tolerant software, and then the system-level design. So for the triple modular redundancy, it uses a voter system where 3 identical logic instances process the same input in parallel. So we have, for example, here module A, module B, and module C all process the same input, and then it goes into a majority voter that then masks a single upset in any one instance. So the voter itself is a single point of failure, and it's about 3 times the area and power cost as the main reason why it's used selectively and not everywhere. So for redundant system architectures, we have cold spares, hot spares, cross-strapping, and functional redundancy. So the cold spare is a backup unit that remains powered off until a fault is detected, then it's switched on, which saves power at the cost of the switchover delay. And the hot spare is a backup that runs in parallel, so it's running hot, or in a low power standby state, which is warm. And then this enables near instant failover for critical functions. Cross-strapping is when the redundant units share buses so that either of them can drive any load, which increases resilience and combines to combine the hardware and the upset failure. So for the cold spares and the hot spares, it's more of like a power versus response time trade-off when you choose which architecture you want to use. They both protect against different failures rather than like as a simple duplication. So in coding memory against bit flips, we have Hamming codes, Reed-Solomon, and then BCH codes. So the Hamming code is a single error correct, double error detect. And the Reed-Solomon operates on symbols rather than bits. And the BCH, it basically corrects multiple random bit errors per word. The Hamming code is more of a default. The Reed-Solomon and the BCH, they matter more as multi-bit upsets become more common in smaller nodes. The overhead versus correction strength trade-off is a real design decision that people have to make when designing these architectures. So memory scrubbing in itself also keeps errors from accumulating. So the way it works is that the code reads the word and what it thinks the reason for this. I was trying to explain what a syndrome is, but I assume you all know what syndrome is. So it reads the word and the syndrome, so like the fault itself, then it detects and corrects the error, then it rewrites the corrected word, and then it advances to the next address. So if there's no issue in this address, it just moves straight on to the next address. But error detection and correction alone is not enough. So that's why a second uncorrected hit in the same word is fatal. So scrubbing basically prevents accumulation. An FPGA configuration memory usually needs it in its own separate scrubber. When we have the error detection and control level, there are some things that this kind of technique cannot catch. So when an SEU corrupts a program counter or a control flow register, it doesn't produce a wrong value. It can just stop the execution. So a watchdog timer is the safety net for this failure mode. So the timer counts down continuously in the dedicated hardware. Then a healthy software periodically resets. If no kick arrives in time, the watchdog will assume a hang and then force recovery. And then the recovery ranges from warm reset to switching to the redundant processor or safe method. So watchdogs basically protect against a corrupted program counter and then stops execution. In terms of defensive coding and state recovery, this is the first software level line of defense. So the software validates everything, and then it always has like a way back to the initial known good state. Checkpointing is like the practical answer to what if we can't like prevent every upset. So different types of this include defensive programming, where range check inputs, valid state machine transitions, and the use of checks on sensors and telemetry values are done before acting on them. We also have assertion-based recovery, where the runtime assertion catches the possible states early and then contains an upset effect before it propagates to the actuators or the downlink data. Voting is what the software is doing in the hardware. So when we talked about triple modular redundancy earlier within hardware, voting, reconfiguration, and handling is basically what the software is doing at the software level. So it reroutes all the bad modules without ground contact, and the health monitoring is then what lets engineers later prove like if a fault was an SEU fault or a hardware failure. Again, we have different versions of this. We have exception and interrupt handling. We have dynamic reconfiguration, and then we have health monitoring and logging. So when we zoom out into the system level, we have containment, we have safe mode hierarchies, and we have autonomous fault detection, isolation, and recovery systems that tie everything together. So the fault containment, it isolates the subsystems. The safe mode hierarchies, it has like layered fallback states. The FDIR is when the onboard logic detects anomalies, isolates the faulty element, and then executes a recovery plan without waiting for like a command from the ground station. And then the ground in the loop is basically like telemetry readings and command overrides that are available for the fault's like autonomy that can't be resolved. So now that we've looked at the techniques, we're going to look at the current challenges and possible future directions. So current challenges include COTS, commercial off-the-shelf pressure, mass power and volume budgets, verification and testing costs, and emerging process nodes. So in terms of commercial off-the-shelf hardware, the cost and the schedules, they normally push small sat programs towards more commercial parts, and most of these commercial parts do not have radiation-hardened hardware within their systems. For the budgeting side, for the structure, electrical power, and structure is mass and rolling. Redundancy and shielding compete directly against the payload. in an already mass-constrained platform. So if you have like a 1U or 2U, it's like, or 3U, you're like, how much can I fit in this to be able to achieve my mission? The beam time for verification and testing is expensive, and it's not common, like it's not readily available relative to new commercial part releases. So the more elements that are like manufactured, we're not getting the same like the speed of testing capability. So for future directions, we have radiation hardened by design commercial off the shelf. We have AI assisted fault prediction, which is the direction my current research is going in. We have adaptive self-healing systems, and then we have standardizations across small satellite systems. For the commercial off-the-shelf components, there's a growing interest for the fabricated parts to be hardened at the design level rather than like a very like special process that is only aligned with that particular component. In terms of the AI-assisted fault prediction, onboard and ground models that learn upset patterns from telemetry are used to anticipate and kind of preempt failures rather than just react to them. But the main issue with this is that software is always going to be like at the level above hardware. So if the AI or if the algorithm or if the model that you're running on your satellite, if that itself in memory in the device is affected by the single particle strike, then your whole AI assisted prediction kind of just like falls to the side because that software in itself was affected. So the key takeaways of my presentation is that single event upsets arise from ionizing radiation that deposit charges past a device critical charge threshold. Small satellites are disproportionately exposed when we consider commercial off-the-shelf parts, thin shielding, and low margin density. There is no single mitigation layer that is sufficient. It's normally like a stack of 2 or 3 that are used in each mission. And then as commercial off-the-shelf process nodes shrink, that is as technology is more miniaturized, multiple bit upsets and new single event effect mechanisms are outpacing some legacy mitigation assumptions, which is an active area of ongoing work. And that is the end of my presentation. Thank you very much.
Okay, thank you. So, do you have any questions for our presenter today?
So I'm Emma. So my first question is related to the radiation itself. So which subsystem could cause or strengthen a radiation effect, or all the radiation effects will just receive from the out sources?
So your question is which subsystem can cause or strengthen radiation effects? What was the second part of your question?
Or all the radiation effect we're receiving from outer sources?
Yes, okay. So radiation is an external phenomenon. So there is no, radiation is not coming from inside the satellite, inside the specific subsystems. Radiation is when particles, external particles, moving at very high velocities, penetrate the components, the atoms of the materials. So there is no specific subsystem that is causing radiation. In terms of strengthening radiation, or I'm assuming you mean that can probably mitigate the effect, which subsystem? There's no particular subsystem. So I talked about it's hardware and software, basically. It's either a hardware level mitigation or a software level mitigation. So it's not a particular subsystem. It's how maybe the structure team decides we want to use this kind of shielding, what they call it, coating or something like that. Or OBC, the onboard computer, decides that we want to implement this software to be able to detect it within these areas of the data that we're getting. Yeah. Does that answer your question?
Yes.
Okay.
And my second question, it's from page 31, I think.
31?
Yes. So, the self-healing system, I just wanted to ask you a question. So, as you mentioned, the AI assisted fault prediction may have some problems due to software malfunctioning. Can a self-healing system recover the software so the AI assisting will be more productive?
So your question is, if you have the two layers of the self-healing system and then the AI assisted system on top, if the AI assisted system has an issue, can the self-healing system kind of reboot that system? Yes, theoretically, yes.
Okay, any other questions?
So let's assume it's like creating a spacecraft, which will work far away from the Earth, like for example from Mars or Jupiter and so on. So my question is, do we need to create additional radiation defense for that spacecrafts?
Yes, because radiation, as I explained in this slide, the intensity of radiation is affected by the location of where that satellite is operating. So if you're operating at low Earth orbit, there's certain expectations that you have that, okay, we're going to have more high energy, like energetic protons, versus if you're going into deep space where you have more like heavier ions being like impacting the satellite. So since the location of where that satellite is going to orbit is important, is a key factor, before you send it into space, yeah, they're different. The way you implement techniques would be different, and the way you plan for possible failures would be different.
So you are saying the orbit matters, right?
Yes.
How about all the orbits?
Also matters, because then, that's not the slide, because then you are considering not only the location, but also the time. So like a type of radiation is total ionization dose, and that's not based on like a direct particle hit. That's based on like how long this component has been in this environment, and how the elements in that environment have affected it over time. So yeah.
Okay. Any other questions? Yeah.
Hello, I'm Atlas, I'm one student. Can you open the page 23 or 24?
23 or
Yes.
or 24.
I think, yeah, they are on the same topic, right? Maybe 23, yeah.
Okay.
Yes. How can we ensure that, like, while writing to flash memory, we can make sure that there is no, like, single event of cells? Like, let's say we have microchip, we are writing to flash memory, right? If there is a communication between, like, microchips, we can make sure that, like, by checking checksum, right? But when it comes to writing memory, flash memory, on the flash memory side, there is no like validation, or can we validate?
Yes, these methods are all methods of validating within the memory. Yeah.
Can you explain it?
Okay, so within the memory, you're not coding in the memory itself. It's still like outside of it, but it's like where, for example, the Hamming code, it detects double errors and then it corrects single errors. So you can write the code where it checks, for a single bit flip in this address in memory. And then if it sees that within the space of memory that you've allocated, then it will what's the word I'm looking for? It will not protect because it's already affected it, but it will like kind of reset it back to the original state. Yeah. So yeah, in the memory, you're not coding in the memory itself. It's still like outside of where you write the code, but you're basically dictating what can occur in the addresses. If it notices certain behaviors in those addresses, then do this function. Yeah.
Okay, are there any other questions related to the radiation effects?
Most university-developed CubeSats do not undergo radiation testing, like one-year CubeSats, and due to their limited size and mass. So how likely our SEUs can cause serious damage to one-year CubeSats?
Could you please tell your name and
My name is Jeffrey Lamboy. I'm a PhD student in Canada.
Okay, thank you very much. This is actually a question that I was asked regarding my research, because when I was talking to my co-supervisor, a lot of what he was asking was, okay, if a reviewer reads your paper on this algorithm to detect what's the probability of this actually happening in space? So that's something I'm actually still researching, like the actual number. But currently, the effects of SEUs, it's not as critical as, for example, like EPS-related errors or within small satellites like one use in space. Yeah, so the probability is, I don't have the exact number.
Okay, but we can describe the likeliness. For example, which among the components, when hit by a particle, would cause the most serious damage to the satellite?
Okay. So maybe resistors that then lead to charge sharing.
But resistors do not have memories.
You said that would cause the most damage to the satellite.
Yes.
So when I was explaining the types of the family, this single event latch up and burnout gate at the most.
I'm asking about SEU.
Oh. Okay. That would cause the most damage.
Yes.
The damage that would cause would still not be like permanent damage that would.
I think the question is something like from the solar proton events, I mean some heavier nuclei, like
Yes.
proton, heavier ions or the nuclei, but heavier ions than protons is very small percentage. In most of the SPGs, it's less than 5% or 1%, and the rest is generally hydrogen ion, that means protons. So those are the ones causing the single events mostly, besides any alpha particles, GSRs. Okay.
Thank you.
Okay.
But it is important, I think, the damage to the MOSFETs, that's the EPS related damages, right? We might observe single event burnouts on those higher orbits, observe that. Those are hard to recover. You need to have a physical backup.
Yeah.
So there's no other way. Okay, any other questions? Over here. I have a question, page 13, maybe. Is it this 13? Well, maybe I'm confused. Could be 18. You are talking about the environmental sources for the radiation, GSR. Could you look
This
at
one?
18 or 20? Not exactly. Okay. My question is, you talk about the small satellites in your title especially. So what is the main difference for this for small satellites and the rest for you while doing this research and taking the environment into account?
But the difference between small satellites and like larger satellites?
Yes, another mission and when you consider the orbits, anything. Because your title says small satellites, right?
Mm.
How uniquely approach to your research in that case?
The constraints, basically. The components are much smaller. The the budgeting for the mass, for the volume, for the power is much tighter. So that's the main difference between
All right.
the main difference in considerations.
So if you want to reroute an FPGA, let's say after a damage, there's a less, probably you have that capability in that small satellite, right? Because that requires maybe extra hardware to be configured to FPGA and your program it. Maybe we don't have it.
Yes.
Because many students are asking if they can do a research to reprogram a subsystem in orbit. Something, those things for instance require extra hardware.
Yes.
For FPGA, I might be confused. I don't know how big actually those extra hardware. But yeah, it's something to consider. Okay, in other questions, we still have 5 or 6 minutes. I have a comment actually. You talk about the how to check the single event upset. Probability, what we did actually, we had some in orbit data before from starting from 4U2. You should check those publications. If
Yes.
you didn't have a reset capability, then we added the 24-hour reset to our satellites. But one important thing, also they made, I was not here, they made a radiation test with a high energy proton source with the same hardware, and then they made a probability function for the single event latch up or single event upset occurs. So you probably require some test results, then do some Monte Carlo simulation afterwards. It is general, most of them is the probability based
Okay.
simulations, and generally the probability is higher after the reset. And as the time passes, let's say you have a single event, you did the power reset. After that, recovery probability is high to happen again. As the time passes, that probability
Goes
decreases.
lower. Okay.
So you might observe something similar to that one. Okay, any other questions?
Regarding the sizes of the satellites, as Professor Major mentioned, which satellites, I mean by the size, can better handle the radiation effect in the single event upsets?
Which satellite within a small spacecraft? Like
Not only small, but maybe it can be even bigger satellites, because I mean bigger satellites we have more complex systems we have and more probable causes of the single event. So that's why.
I do not have an answer for you on a specific size of satellite. I can better.
It also doesn't make sense to ask the question like that. I'm not saying your question is bad, but it is correct. But how you view is you have a critical components in the presentation. It's already listed like flash memories, MCUs, and what else? The MOSFETs. Then you have all the
Semiconductors.
component size and the cross sections. You need to study over those, like how many you have. You might have a larger satellite, but you have less of those components maybe. Then
Yeah, and also like you might have a bigger satellite, so you might have the space for redundant systems, but then maybe that bigger satellite is operating in an orbit that has more the different types of radiation that a smaller satellite in a lower orbit does not. So it's subjective.
Mhm.
Yeah, subjective.
Yeah. Maybe you can count also multiplexers.
Yes.
Okay.
They count as logic, their logic circuits that can be affected.
Yeah. Any other questions? So we have like one final question and ask. I know some of the students are really interested in the fault-related fault detections, but you talk about both onboard and the ground. Then let me ask you the closing question. Can you go to your key points in the last page? Maybe one page before, you were talking about the AI-assisted fault predictions, and it actually is related to your research, right?
Mm-hmm.
How are you seeing this field? Like how it could evolve in your eyes with the latest development?
I'm thinking of the word that I am. I can't remember the word I'm looking for, but basically it's like I am apprehensive of software ever surpassing the hardware level mitigation techniques. So I think that in terms of analyzing the data, in terms of like training to be able to maybe detect slightly earlier, like we can get somewhere, but like the hardware level detection will still be faster.
Then let me ask you this way. Would you trust an AI on board to take critical decisions for you?
If it was like part of a redundancy system, yes, because somebody that can take a critical decision is better than nothing at all.
Mm-hmm.
So if it was part of a redundant system, yes.
Okay, so that is your kind of job right now, to convince system engineer or a project manager to include
Why
a
they
system on
should,
board like
okay.
this. So you should come very strong on that one if you ever want to. Okay, thank you very much. This was a very interesting presentation.
Thank you very much.
Okay, for the PhD students, I will sign your documents now.